Hey guys, what's going on? We're ready for our next talk. We're almost down to the end, and it's going very well, I think. So our next talk is basically called DoS, Denial of Shopping, Analyzing, Exploiting Physical Shopping Cart Immobilization Systems by Joseph Gabay. All right, this is his first talk. Please give him a big shout out. All right, and here you go, Joe.
Thank you very much. Yeah, not only is this my first time speaking at DEF CON, this is actually my first time attending DEF CON. And even at the safe mode version of it, this has just been an absolutely fantastic experience, and I've met some really, really amazing and really, really smart people. So I'm having an absolute blast, and it's a real pleasure to be up here. So without further ado, welcome to DoS, Denial of Shopping. Analyzing and exploiting physical shopping cart immobilization systems. Before I get into the talk, I have a brief disclaimer. This is a personal project. I've done this on my own personal time with my own personal equipment for my own personal reasons. This shouldn't reflect on my employer, my friends, or really anybody else but myself. Now, with that said, let's get into it. So, for those of you not familiar with shopping cart security wheels, they're basically invisible fences, but for carts. They're designed so if you try to take a shopping cart outside of an approved area, usually a parking lot, or some of them have them in the front of the store, one of the wheels will lock up, preventing you from taking the cart any further. It's not something that you see every day. Usually you only see it in supermarkets that are pedestrian accessible, where they're worried about people walking off onto the sidewalk with shopping cart wheels. But the first time I saw them, I got very, very curious. So at this point, most people have two questions. The first one is, who am I and how did I get in here? The answer to that is, I'm a hacker and I'm a hacker. My name's Joseph Gabay. By day, I design robots. By night, I hack shopping cart wheels. Bit of a weird tagline. I'm still workshopping it, but I'll take it where it is. For my day job, I design robots and robotic systems, and for fun, I do a huge variety of things. I usually like tinkering and taking things apart, and this project, like many of my others, is really just a vehicle to learn new skills and figure new things out. This was a great foray into radio frequency reverse engineering and the associated things, and that's what I'm here to talk to you about today. The second question people usually have is, why shopping cart wheels? For me, I hadn't seen these systems for a very long time until I came to Boston, where I'm living now. And the first time I saw one of the signs warning of these, I got really, really curious. I couldn't figure out how they worked. How do they know when they're outside of the approved area? How do they actually lock the wheel? Are they using GPS? Do they have a battery system? Is it all passive? There's a huge, huge amount of design challenges for a system like this, and I knew that inside there were going to be some very clever solutions. But why did I choose to hack them and go through all this effort of taking them further apart? I think Terry Pratchett said it best when he said, it's not worth doing something unless someone somewhere would much rather you weren't doing it. And I think this really speaks to the ethos of a lot of us here as hackers. Some very smart people spent a lot of time and a lot of money designing a system to prevent someone like me from walking out of a store with a shopping cart. I never really wanted a shopping cart, but I feel it's important to me as a hacker and as a techie that I have the knowledge that if I wanted a shopping cart, I could have one, right? And you see it all over. I see it similar to lock sport, competitive lock picking. It's never about what's behind the lock. It's about the knowledge that you can defeat a technical security challenge that somebody else has set out. And Gatekeeper Systems in their marketing materials say that it's about $180 million a year loss center. So there's decent financial incentive to get this right. So it should make for a good challenge. And when I tore it apart and saw what was inside, I was definitely very impressed. So let's say we want to learn about how a random device we have works. In this case, it would be a shopping wheel, but this is a good starting point for any sort of reverse engineering work. There's a couple really good resources I checked out first. FCC.gov is always a gold mine. Any device that uses radio frequencies and is going to be even remotely available to the public has to have a huge, huge amount of information disclosed to the FCC, mostly test reports, information about what frequencies it uses, what modulation it uses, and all of this information is public record. You can go to fcc.gov, type in the FCC ID of a device, and it has to be printed on the device. If you look at the outside of these wheels, there's a little engraved in label FCC ID W3Z whatever. And you pull it up and you get all of this information, including user manuals for the devices, which have a lot more information than you'd expect. Other sources are Google Patents for any patented device. If you want to see how internal mechanisms work or get an idea of the general principles of operation, Google Patents has that all laid out if you know how to search. And in this case, this is specific to this project, but other hackers. There's a French group of hackers called Temp Lab who back in 2008 were playing around with these shopping cart wheels a little bit. They didn't get as far as I have, and they focused mostly on the signal capture and replay. But they were the folks who gave me the inspiration to attack this from an audio amplifier angle rather than a radio amplifier angle. So I do owe them a great deal. I'm standing on their shoulders in some ways. I have a link to their site and their work at the end of this talk, so please check them out. So how do these systems work? In normal operation, you have a buried wire around the perimeter of the parking lot or installed into the supermarket or wherever you want to basically have the cart check in with something. That wire is pulsing out a very low frequency radio signal, and as we'll learn later, it's 7.8 kilohertz, which is very, very low for most radio things. At that point, it's less of a radio system and more of a magnetic loop system where you have two magnets coupled to send signals. And as you'll recall from physics class, when you have a wire and you pump a current through it, you get a magnetic field going around it according to the right-hand rule. And that's what's going on here, is they're pumping electricity through that buried wire. You're getting a magnetic/radio that kind of gets weird in the near field area. You get that signal out, and the cart is listening for that. When the cart senses that it's been crossed over the boundary, an internal mechanism activates and prevents you from taking it any further. Past that point, the store staff has a remote called a cart key. We'll look at that in a little bit. And they can go by and they can unlock the wheel and return the cart to service. And in this talk, we'll be talking about ways to pretend you have a cart key when you really don't. So let's take a look at this wire. I was fortunate enough to live somewhere a few years ago that was having their sidewalk redone, and they used one of these systems. So I was actually able to see up close and personal what that buried wire looks like. And you can see in that very sloppily highlighted area, that little bit of wire, I believe that is 14 gauge wire. I'd have to check the spec again. It's in the user manual available on fcc.gov if anyone's curious. But that's the actual wire that's sending out that signal that causes the carts to lock. So let's take a look at what's going on inside these wheels, because they're a very clever piece of engineering. There's two parts. You have the outer housing there, and you'll notice that there's the little ridges on the inside diameter of that housing. And then you have the inner assembly, and that houses all of the electronics and the other parts of the locking mechanism. The important thing to note here is in that lower assembly, you have a flexible ring with ridges on the outer diameter. And when you combine them, they look like this. Now, the key to the locking mechanism is that little plunger you see in the top here. So when that little plunger is driven by a motor, we'll talk about that in a second, it causes that inner ring to expand and contract. And when it's expanded, the ridges on the outer diameter of the inner assembly lock with the ridges on the inner diameter of the outer housing, I said that right, thank God, and prevent the wheel from turning any further. So it's a real clever mechanism, and it doesn't require any sort of external braking thing. It's all internal, which is pretty cool. So taking a look at that inner assembly that houses all of the electronics, we see three main parts. There is a 3-volt lithium battery. This is a non-rechargeable battery. It's the same sort of battery for the coin cell that you see in your badges here, just a 3-volt lithium. Non-rechargeable, all of this is weatherized and super sealed. It was a pain in the butt to get taken apart. I still have a couple cuts on my hand from it. Blood, sweat, and tears went into this project. But yeah, so once that battery is done, the wheel stops working. Most microcontrollers nowadays can run on ultra-low power modes, basically waiting for a wake-up signal of a radio. So the lifespan of these wheels is actually fairly long, assuming you're not doing any high current application like driving that motor a whole bunch. Underneath that, you have the PCB assembly. That holds all of the radios and the electronics as well as the microcontroller. We'll do a zoomed in look at that in a second. And lastly, under that, you have a little DC motor, and that connects to a gear train, which actually drives that plunger up and down. Taking a look at the PCB, we have a couple cool things going on. First of all, there are two separate antennas. Highlighted up above, there's the 2.4 gigahertz antenna. That is just done on the PCBs. That's really all you need to do it. And the microcontroller, which is a Texas Instruments CC2510, has a built-in 2.4 gigahertz transceiver, so you don't need any separate radio chips or anything additional to support it. You basically just connect the antenna to the microcontroller, and you're off to the races. The second one you can see on the backside, that little black cylinder, is an inductor. And that inductor is acting as the antenna for the 7.8 kilohertz signal. At that low frequencies, you're not really in the antenna range anymore, but that's basically serving the same purpose of picking up that magnetic signal. And off to the right of the microcontroller in the top picture, there's a whole bunch of transistors and amplifiers. I'm not entirely sure how it works, but that's very likely an amplifier circuit that's amplifying the very weak signal you get from that magnetic coupling and turning it into something that the microcontroller can interpret and use. If anyone's got an idea of how an amp like that would work, grab me after the talk. I'm very curious. But moving on, we have that microcontroller. We have below the microcontroller a couple more transistors acting as a bridge to drive the DC motor to lock and unlock it. And lastly of note, to the left, we have a JTAG port. JTAG ports are used for programming and debugging the microcontroller. You can do some other fun things off of it. It is notable that they did not implement firmware readback protection into the microcontroller. So you could hook up to this JTAG port and dump the firmware off of this wheel for later nefarious purposes or educational reasons, your pick. I haven't had the time to do this yet, so it's left as an exercise to the reader. If anybody does happen to do this and find something interesting, please, my email's at the end of the talk. I'd be very curious to see what you find. So now that we know how the wheel works, it's time to start capturing some of the signals and seeing what we can do with them. I decided to start with capturing the signal coming out of the buried wire in the parking lot. There's a couple challenges around this. The first one, as I've mentioned, is that the signal is at 7.8 kilohertz. This is very, very low when it comes to radio stuff. And most radio amplifiers and software-defined radios don't really support frequencies below 1 megahertz, which is 2 orders of magnitude too high. So that's a problem. The other problem comes from finding an antenna to work with this. Generally in radio applications, and I'm not a radio engineer, so I surely won't get this perfectly, but generally you want your antenna to be close-ish or an integer multiple of your radio frequency, your radio wavelength. The wavelength of this signal in this case is about 32 kilometers, so despite my best efforts, I wasn't able to build a tens of mile long antenna for this project. If I did, I'd have a great transmission radius and I'd lock every shopping cart on the East Coast, but a little outside of my budget for this talk. Now, this is where the folks at Temp Lab were a huge boon because they realized that 7.8 kilohertz is well within the audio range. So you can use just regular audio amplifiers and audio processing tools to deal with this signal, and you don't actually have to treat it as a radio signal. So this is where I would like to give a brief apology. Do we have any RF or electrical engineers in the audience? All right, I'm sorry, guys. I'm not really sorry. Please send your hate mail to me after this. I'd love to learn how I could have done this better, but I'm about to do some very janky radio things right here. So I needed to capture this signal, and I had an idea. I built myself a loopstick antenna using a ferrite core, a bunch of magnet wire, and a cordless drill. I did do a smart thing, and after consulting the ARRL handbook a whole bunch, added a couple tuning capacitors and tried to do a decent job at it, and I wired all of this into a 3.5 millimeter headphone jack. You'll also notice there's a resistor in there to trick my phone into thinking that that jack belonged to a microphone and not a set of speakers. I think you can see where this is going. So I decided to take a little field trip and see what could go wrong. So I went to my local redacted store that has one of these systems, and I plopped this monstrosity down on the seam where you could see this wire, and I opened up a audio spectrogram app. And what do you know? There's a signal. If we zoom in a little bit, we can see that, just as expected, we see a signal at 7.8 kilohertz. This somehow worked. We also see one at 15.6, but that's just due to resonance. That's totally expectable. And because it was an audio app, I could open up a voice recorder, and I recorded this as a MP3 file, and I loaded it into Audacity. And here we go. Here's the signal. You can see from here, it is the signal to lock it follows a pattern where it's an 1/8 second series of pulses followed by an 1/8 second rest period, and it just keeps repeating that pattern 4 times a second forever. And that's what it takes to lock a shopping cart. If we zoom in, we can see, and first of all, I should note that there's no frequency shift modulation. This is all just happening at 7.8 kilohertz. It's very, very basic, but this is what the message looks like. We have at the start and end of it some longer pulses. Those are start and stop bits to let the receiving end know when the message is starting and stopping. And in the middle, we have 8 payload bits. Now, if you were a shopping cart wheel, this would be some very exciting news, but 10001110. And that is all that's right. That's all that's required to lock a shopping cart wheel is sending this at 7.8 kilohertz. So that's all I could get from what was easily available. To go any further, I needed to get some more equipment. Now, through the magic of eBay, I honestly could not believe it. I managed to get my hands on one of the actual cart keys that the store employees use to control these carts. Now, interestingly, about this, and this is something that I learned from both the fact that there's a 2.4 gigahertz antenna in hardware, as well as some things that I learned from checking out the other applications on fcc.gov from the same company, because one company shares the same 3 or 5 letter start code, so you can see an entire family of products on fcc.gov, and that's how I came to know about the existence of these, that it broadcasts the unlock signal at 2.4 gigahertz. And what that means is there is a long-range, easily transmittable control method for these. And we're going to explore those in a little bit. But right now, I was mostly curious about what it's doing on that low frequency band, the 7.8 kilohertz. So I repeated this, and the 2 things I got doing this with a remote instead of a parking lot is a lot fewer weird looks, as well as these 2 beautiful captures. Now, they're slightly different and they look different, but each one of those kind of bars is actually just several of those quarter-second pulses up close, and they just have a burst of them and a longer space and then another burst. If we zoom in and look at the lock and unlock signals in comparison, we see that they have the exact same format, the same start bits, the same stop bits. And those of you who are particularly observant or are reading the PowerPoint presentation will notice that the unlock signal is just the logical inverse of the lock signal. So where there's a 1, there's a 0, and where there's a 0, there's a 1. Just an interesting bit of symmetry, I noticed, and that probably aids in preventing signals from being mistaken, to make the lock signal as different as possible from the unlock signal. So we have all this. Let's try a replay attack. A replay attack is basically where you take a system that doesn't have any sort of fancy authentication. There's no authentication in this. It's not incrementing a number. It's just the same signal being broadcast over and over and being received. I suppose Gatekeeper Systems, who's one of the main manufacturers of these, didn't anticipate anybody taking an interest in their systems and wanting to reverse engineer them. Who would have thunk? But anyway, so for a replay attack, what I wanted to do is take the signals I just recorded and through some method rebroadcast them and see if I could get the wheel to respond to my commands pretending I was a cart key. I ended up using that antenna that I built previously. I just wired it in as a speaker instead of a microphone, and we'll see the results of that in a second. But here's an interesting aside. Again, credit to TempLab for this discovery. But you can actually use a set of headphones or your phone speaker as a crappy antenna to control these cartwheels. When you think about it, all a speaker is a coil of wire connected to a membrane to produce sound. Normally, the little bits of electromagnetic signal that comes off of this is considered a nuisance as parasitic EMF. But in this case, that's the kind of signal that we're trying to emulate here. So yeah, you'll make a god-awful screeching sound with it, but you can control and do whatever you want with these shopping cart wheels. And there's a link at the end of this talk I have on my website, the 2 MP3 files you can download, load them on your phone, turn your speaker on, hold them up to a wheel, and you can get them to lock and unlock. Oh yeah, use the powers for good or evil. I'm a hacker, not a cop. So let's see this working in real life. And this isn't with my phone or speakers. This is using the loopstick antenna, just wired as a speaker. But yeah. So here I am hitting the lock signal, and you can see that wheel expanding when that would normally lock it. And then when I hit the unlock and play that signal, it unlocks and recontracts. I really have to give it out to Gatekeeper Systems. This is a really, really clever design. I really like how they did this, and I feel bad for just doing what I'm doing to them, but only a little bit. So, as any good hacker would ask, now my question is, how far can this go? You know, what is the longest range I can perform a replay attack like this? And I'm sure some of you are thinking where this is going. So I tried a few things. I picked up this absolutely massive solenoid coil at the MIT Flea because what's bigger than a loopstick antenna? A bigger loopstick antenna. I also tried some different external audio amplifiers rather than just using my cell phone's built-in one. I got a 10-watt audio amplifier and hooked that up, and I was able to get really 2 to 3 feet effective range with that setup. Past that, I was really fighting against diminishing returns for a few reasons, and unfortunately they're kind of butting up against those pesky little laws of physics, the one law I'm unable to break. But basically what's happening is it's hard to transmit things, especially at frequencies that don't like to be transmitted at. Loopstick antennas are okay receivers, but they're not particularly good at transmitting signals, just based on their geometry and how they work, as well as the fact that with radio, you're dealing with the inverse square rule. So to double your range, you need to quadruple your transmission power. And you can see how, if you want to say, send this signal 1,000 feet, how absolutely insane that would get and how quickly it would scale up. So unfortunately, there's not too much you can do at long range with this. Which brings us to the 2.4 gigahertz signal. 2.4 gigahertz, which is what Bluetooth and Wi-Fi all work at, is much, much easier to broadcast at, obviously. This, you can just use regular off-the-shelf equipment to sniff. In this case, I used a HackRF, which is an SDR that goes from 1 megahertz to 6 gigahertz. Tremendous range. They're made by Great Scott Gadgets. Great company, great tool. But this should be more than enough to let us sniff that 2.4 gigahertz control signal. So that's exactly what I did. I loaded up GQRX, which let me scrub through the channels, and I centered it around 2.4 and just looked around while pressing the button until I saw a signal, and eventually I saw this. So you can see we've got some sort of signal. It's a little hard to see what exactly is going on, but it's happening across 2 frequencies, and that tells us it's likely some sort of frequency shift keying that's happening. But more importantly, we know the center frequency and we know the range, so we can take a bit more of an exact look in that in something like Ultimate Radio Hacker. So I did the same thing and took the same capture in Ultimate Radio Hacker, and this is what it looks like. So you have the 3 pulses, you have a series of 3 pulses here, and it's happening across 2 different frequencies. You have low, high, low, low, high, low being repeated. And that's our signal. Unlike the 7.8 kilohertz signal, which was an 8-bit payload, this signal is just 3 bits. It uses 2FSK modulation, as I've previously said, and up here is just the actual details on what frequencies it uses in case anybody's curious about those technical details. But it's just broadcasting 010, 010, and because I wanted to be a little bit cheeky, I was able to export this capture as a WAV file and load it into Audacity, albeit at an absolutely absurd sample rate of 8 megahertz. But turns out Audacity just lets you input really big numbers into its text fields and it just works. So from here, I was able to slice and dice the audio waveform just like any other audio signal and rearrange things. I was also able to make synthetic commands because I knew the two frequencies and I knew the timing and duration. So I was able to reconstruct signals from pure tones. And then I can export it as a WAV file, and Ultimate Radio Hacker will actually let you play a WAV file through a software-defined radio. And that's exactly what I did. So here's what the signal that I reconstructed looks like. It's the two frequencies we discovered earlier, and I just measured out how many microseconds each one was, as well as the interval between them. And I just made this 3-bit pattern and set it to repeat forever. And I played that back to the HackRF. And this one takes a little bit longer, but we can see what happens. I go ahead and click play, and if we go over to the workbench here, I have a wheel that I modified to run off a benchtop power supply. After a few seconds, it closes. Now, the interesting thing about this method is 2.4 gigahertz is incredibly easy to broadcast. I was able to, unlock this wheel from across my workshop, and quite frankly, I'd be able to do it basically as far as I was able to transmit a Wi-Fi signal, which is pretty far, especially for those who have worked with microwave systems before. You can get 2.4 real far, and real directionally too. Now the question, oh yeah, I'm in. Now the question is, can we lock carts on 2.4 gigahertz? Unfortunately, I think the answer is no to this. I tried every possible 3-bit permutation, so in Audacity I constructed 000, 001, 010, etc., and I tried all of them. None of them triggered it to lock. This is probably working as intended, because if I were Gatekeeper Systems, I wouldn't implement a locking function over something that could go ultra long range. So this was probably done intentionally, either to prevent accidental malfunction or to prevent malicious interference, we'll call it. But it is interesting of note that these wheels do have some advanced functionality that's unexplored. This was on the back of that cart key, and it lists some other codes. Based on what I was able to find on the FCC filings, it's very likely that these codes operate on 7.8 kilohertz, and it would make sense because you have an 8-bit payload there as opposed to a 3-bit payload, so you can actually fit numbers like 23. But Gatekeeper Systems, from their marketing material, does have some other interesting features, like you can set up a cart to lock when it exits the front door if it hasn't gone through a checkout lane first, to prevent people from filling a cart and running out. So it's likely that these functions are meant to interact with that advanced functionality. I haven't really seen any of that advanced functionality in the wild. I've mostly seen the systems that lock when you take it out of the shopping cart area, but these systems are mostly designed to be invisible unless you're actively looking for them, and I guarantee you everyone in this room will start seeing them everywhere from now on. As well as, I don't know, it seems like a lot more expensive a proposition to have a system like that with a lot more ways it could go wrong and impact a customer experience. So I wouldn't be surprised if that was a more uncommon method or one that didn't work with every sort of wheel. So that is all I've got to talk to you about shopping cart wheels. Like, thank you all for letting me talk to you about shopping cart wheels for 20 minutes. This has been great. Here's a list of all the references as well as some of the tools I've used. I'd also like to give a huge special thanks to the folks at the Electronic Frontier Foundation and their Coders' Rights Project. As I was doing this, I had a few questions on what was exactly legal for me to explore and what was legal for me to share with you fine folks. And I reached out to them and they got back to me and they answered all of my questions, and they were absolutely great. If any of you are working on any sort of reverse engineering or vulnerability disclosure things and you have questions and want to make sure you do it the right and legal way, reach out to the EFF. They're great and they're here for hackers like us. So thank you all for coming. If you have any questions, anything I missed, or anything I've done wrong, and oh boy, I've done things wrong. You saw that RF setup right there. You can send your emails to joseph@bgaydocrime.com. For any professional inquiries, joseph@tethys.cc may be more to your liking. I'm at Stopping Cart on Twitter. I post new content yearly. And as I said before, the MP3 files to lock and unlock shopping cart wheels are available at bgaydocrime.com/carts. Thank you, thank you. I'll be sticking around the con floor for a little bit longer. I can take some questions here. I believe I have some time, or if you want to catch me after the talk. But any questions? Going once, twice. Bueller, question? Pardon? I've been advised by the EFF not to discuss that. Yeah, one of the big takeaways from this is if your goal is to walk off a parking lot with a shopping cart, there's a lot easier ways to do it. I will bring up the fact that transmitting at 7.8 kilohertz is very difficult, and you're dealing with that inverse square law. So imagine the effective range of a buried wire broadcasting this signal. It's not very high. Realistically speaking, you could just lift the wheel up 4 or 5 inches over that line and it wouldn't trigger it. So like, this is an academic experience in hacking. You know, if your end goal is a shopping cart, there's a lot easier ways out there than hauling out your HackRF and doing some fun hackery. I mean, I'm not judging you. You're welcome to do it however you want. I'm the one who spent like 2 years researching this on and off and like playing with it. So I'm in no position to judge any of you here on what you do with your shopping carts. Yeah. All right, if that's it, thank you all for coming and listening to my talk.